All right. Okay, so you guys all know that tonight is a big night for the class. We got midterm. Very exciting. So today, mostly what I'm thinking about doing is answering questions if you have any about midterm-related stuff. I'm going to make a few comments, too, about how regrades work. I forgot to mention that on the review last week about how midterm regrades work in this class. So I'll talk about that a little bit today. And then if there's not that many questions, I'll probably give you some introduction stuff we're going to get into next week. Sorry? Was there a question? Oh, yeah, right. No new material. So, yeah, so the thing is, starting next week, we're going to get into Rotary Motion, which is not a tonight's midterm. I'm going to cover that from the get-go, from the beginning on Tuesday next week. So you don't have to worry about missing anything or today. But the thing is, if all you guys are here, so it doesn't matter. People aren't going to worry about it. But the stuff I'll cover today about Rotary Motion will be to get you started thinking about it if you get that far. I'm going to cover it next week from the outset. But it always helps to see stuff early. Always helps out. It's going to show up in the second midterm. That's only like 4 weeks away or whatever it is. Coming up fast. So I know this class goes quick. So today, regrades. So let me mention that real quick. The way regrades work, if you haven't been in one of these classes, well, actually, it may be different policy here than it is in your chemistry or biology classes. The way it works here, you'll take the midterm tonight, right? It'll be graded by, there's 4 problems on the exam, as you know. Each problem is graded by a different grader, and the grader is responsible for all, whatever it is, 350 students, problem number 1, or all problem number 2. So the same person grades the same problem on every exam to make it fair. That way, there's not going to be discontinuity between different people's exams. The same grader will grade all problem number 1s, or all problem numbers, whatever it is. Then what happens is the points are tallied and scores figured out, and you get your test is handed back in your section, right? When you get it back in section, you'll have a chance to look it over and make sure that there are no errors. The most important thing for you to do is to make sure the points add up. Like the most common sort of an error that might result in a change in your grade to a regrade would be you discovered that somebody added up 25 plus 35 and got only 15 points or something in front. So just make sure that the points add up. And so the GSI, the last 10 minutes of class will say, okay, put away your pens and pencils, you look over your exam. You may also look over it though for other kinds of errors. If you see some other grading mistake that was made, like and you think you deserve more credit than you got for a given problem, you can go ahead and request a regrade. You can't do that once you walk out of the room with the exam. So when the exam's handed back, if you see a problem with the exam, articulate very clearly and succinctly in writing what the problem is. Once you tell the GSI that's what you're doing, he or she will say, all right, write down your concerns, or say exactly what you think the problem is, and then it gets turned back in, and that goes back to the original grader to reevaluate whether they made a mistake in the grade your exam. I'll warn you though, don't just, like some students have a strategy, they just want to do regrades for everything over and over until they just, in the hopes of just getting more points. If you don't have a specific concern, right, you can wind up, it can happen that the grade can go down even after a regrade. This happens with some frequency, because when the grader goes back to look at it again, he or she will look at it with more scrutiny, and then goes, oh yeah, I sort of cut on a break over here, but now they look at it more closely, I see that there's a problem. So you can actually have your grade go down for regrades. So don't just do regrades for no reason, with hopes you'll get more points every time you resubmit it. You're going to get, you can have your grade improved if there's a real mistake made in the grading. And like I said, if you see an addition error with the points, that's just unequivocal. There's no debate about it as long as there's no, we'll go out together and get it right and I'll get the right score on there. So anyway, that's how regrades work. And it happens the first section you go to after they're graded, which may be early next week, probably mid next week, somewhere in there. Anyway, so that's regrades. In other words, you come to me, then I can do it. I'm out of the loop for that kind of stuff. Yes. No, yeah, so regrades are very specific. If you have a concern with problem 3B, say, it'll go back to the grader for problem 3. It's not going to go back to the graders for problems 1, 2, and 4. They'll just read it out to your problem. So yeah, regrades don't reevaluate the entire test. They just reevaluate the part that you thought had a problem. Yeah. Anyway, yeah. Any more questions about that kind of stuff? Business? All right. In terms of, so what about the material? So do you have questions about the material? Like for one thing, I'm curious to ask you, what is it you're most concerned about in terms of material on the exam? Like what's the hardest part of the exam going to be? Circles. Yeah, circuit of motion. So there's a couple different kinds of circuit of motion. What are they? Uniform and non-uniform, right? What does uniform circuit of motion mean? Constant speed. It's not constant velocity. For uniform circuit of motion, it's not constant acceleration either, but is the magnitude of the acceleration constant? Yeah, it is. I have some good questions in office hours about non-uniform circuit of motion and how to relate it to uniform circuit of motion in some special cases. So if you have a ball going in, like a roller coaster, right? You got the roller, one of my favorite demos. You got the roller coaster going, and it's at the top or the bottom. So a student asked me, wait a minute, right at the top. Oop, didn't quite make it there. Let's do a real circuit of motion. Oh, it always gets away from me. Right at the top. So which way is the acceleration pointing right at the top? Straight down. Even though this is not an example of uniform circuit of motion as it goes around, at the moment it reaches the top, the normal force points straight down, and so does the force of gravity. So the net force on this ball is in fact straight down. And so is it speeding up or slowing down at the top of the track? Speeding up, slowing down? Neither. Can't do both. Neither. So it's as if it's doing uniform circuit of motion right at the top of the track. Same thing for right at the bottom of the track. At that instant in time, the acceleration is exactly perpendicular to the direction of motion. So that means at that moment it's as if it's analogous to some ball that was following a different circle that momentarily is. Yeah, it has exactly the same acceleration, the same velocity, everything's the same about the motion of the ball at that moment in time, as if it were doing uniform circuit motion. But anyway, but in general, if you're in different locations, that won't be true. The acceleration vector will not point straight to the center of the circle. Will it point a little bit higher or lower, the acceleration vector, than the center of the circle? A little bit above or a little bit below? A little below? Does it matter which way it's going? Does it matter if it's going that way versus that way? No, it doesn't matter. That's right, it doesn't matter. What matters is the direction of gravity, which points down. If you think about the trajectory of this ball, if I let it go and it goes around, let's see how I say this. If I let it go around and then say, well, what if I did the opposite trajectory? Just time reverse the whole thing. It would in fact be experiencing all the same forces at the same points along the way, just in the opposite order. The force is the same. It doesn't matter if it's going up or down on the track. It's gravity down. Because gravity doesn't care which way you're moving, right? The normal force doesn't care which way you're moving. The strength of the normal force and the direction of the normal force has to do with well, the direction for sure has to do with the shape of the track where you are, and that doesn't depend on which way you're going, as long as you're staying on the track, right? And the magnitude of it, well, okay, it's a little bit trickier, but it turns out it goes through the math. It doesn't matter which way you're going. Yeah, okay, cool. And then for uniform circuit motion, that's constant speed. Usually that comes up in the context of either you'll have like the Ferris wheel kind of problem, like you see in past midterms where you're going at constant, your speed is constant even though you're in a vertical circle. But it can also happen, right, if you're going around a track that's horizontal, where the speed doesn't change. And that's a little easier to think about in terms of acceleration. It's always pointing right to the middle, right? Yeah, I got this demo out actually for stuff I might introduce a little later about circuit motion. Yeah. For tangential, and you mentioned the x component. So if you define your x-axis to be tangential, saying that right, to be along a tangent line to the circle, then yeah, you'd have zero acceleration along that direction. No acceleration, no component of acceleration along the direction of the track if you're in uniform circular motion. Or for that matter, if you're in non-uniform circular motion, but you're at the bottom of that track right there. So the forces are all vertical and you're at the bottom, right? So in those cases, yeah, there's no acceleration. You're not speeding up or slowing down. So speeding up and slowing down, what is that? Speeding up means you've got some non-zero tangential acceleration. right? Which is in the direction that you're moving already. Speeds you up. If it's in the opposite direction you're moving, it slows you down. What other topics are coming up, or that might be on the exam that are, yeah? Conservation of energy. Yeah, so real useful. There might be, it may even be that there's a problem where you could have solved it, or you could solve it a different way, maybe with a kinematic equation. But if you can use conservation of energy, at least for me, whenever I can use it, I use it. It's usually faster, and I make fewer mistakes. It's easier to think about the problem if you've got some complicated trajectory going on. So as I remember, I have to think back a little bit about the exam, I wrote it a few nights ago. It could well be that, well, for sure there's conservation of energy somewhere on there. And I think that there are problems where you'll have an option, and you usually do, about how to solve it. If you can do it with conservation of energy, at least for me, that's how I would do it. And just whenever you do that, remember, you have to make sure there's no external forces acting, or if they are, include a work term. You do friction or whatever. Right? When you have conservation of energy, you always say, all right, I've got all my final energies, right? I got my kinetic energies, and there might be multiple objects in the problem. So maybe you'll have a kinetic energy of one object plus a kinetic energy of the second object. So maybe there's a sum of kinetic energies. You might have a bunch of them, right? And then you've got, maybe there's potential energy due to gravity, right? And maybe that's true for a bunch of objects. You have a sum of those, right? These little sigma signs to mean summation. And maybe there's springs in the problem. Guys, I did myself in the room for all the stuff that might be there. Oh, and I wrote I. So I here means for each object. Maybe I shouldn't use I for initial then, just to make it so I don't mean this to mean initial. I mean for each of your objects, right? Where I is an index over each object in the problem. And you have other stuff too. You don't have room for it, but other stuff too. So this is final. Subtract the initial, right? And then that equals work from external sources, right? Forces from other things. And if you have potential energy due to gravity, like crammed in over here, right? If you have it here, make sure you include it here, and do not include it in the external work, right? So you can it's just as valid to include work due to gravity and not include potential energy terms due to gravity. That's perfectly fine. But don't do both and don't do neither, right? Make sure you only count it once. Otherwise, and by once I mean either it appears in both of these locations or it appears in that location. I don't mean there, or there. It's got to be in there, there. But if you have it in both these spots, then don't put it there. Yeah, and the same thing for springs. You can also think of a spring as exerting some external force on a system, or you can think of it as a reservoir for energy, right? You compress the spring or you extend it, right? Springs, what about springs? One thing that trips students up a lot is they have this expression, you've got the formula written down on your sheet, and it's on the exam and all this stuff, for Huff's law, right? Force from spring, right? Let's say in the x direction, there's a minus sign, right? It's a restorative force. Say, oh yeah, it's some constant k, the spring constant, times, now I usually write it as delta x. Now the thing that's tricky for a lot of students is they'll look at this and they'll forget what delta x really means, right? So when you have a spring that has some equilibrium length, right? What does delta x equal? If the spring is at its equilibrium length right now, then what is delta x for that situation? 0. Yeah, it's 0. That means that the object at the end of the spring is exactly where it would be if the spring, well, and it is where it is. There's no force being exerted on it by the spring. So there's some problems from past midterms too, where you were asked to calculate things in sort of a different order than you used to. So some students are very comfortable. I'll give them k, I'll give them delta x, and then I ask them to calculate f. Even if I give them this by saying, oh, here's the length of the spring when it's unstretched, and then here's how long it is right now. Tell me what the force is. No problem, But then if I phrase the problem a different way, where there's a spring in the problem and there's some force given, maybe, where you calculated in part B, and now you're going to apply it in part C or something, so you can know the force. And maybe you can infer this, and you're asked to find that, or you're given this, but asked to find that. Some students won't be able to. They don't know how to proceed, even though they can handle this, no problem. If I go give them that, and they solve that. So, and that's a general issue for this class, right? There's going to be problems on the exam, most likely, that are not being presented, and just like in your homework and like in class exam, that are presented in such a way that it's not like you plug in stuff on the right-hand side of the equation to get the thing on the left, right? Sort of the vanilla version of the physics problem that we all crave. Easy, right? Someone gives me stuff on the right, I plug it in, I get the thing on the left. That's the way, it's the easiest way to do it. There are some problems that will be deceptively simple, and some problems that might be a little deceptively hard, and that it might look like you can just plug in track with one equation, but if you think about it enough, maybe there's 3 equations you need to combine. In other cases, it might look like you need to do it with 5 equations, but there's a trick. Maybe involving conservation of energy, some other sort of a rule like that, where you might have thought to do it using conservation law, where you only need one equation. So it can go both ways. So when you're on the exam, think about it before you plunge in on each problem a little bit. And it's okay to get started down the path and you realize, there's a better way to do this. I can do this really quick. You may want to do it 2 different ways to check your answer. But whatever you do, make it really clear what's being graded and what's not. If you got 2 things going and you don't finish one, make sure that the grader knows. Box your answers, right? So, and make it clear what steps led up to your answer. So they know what they're grading, right? And don't leave anything down, it's not true. But anyway, yeah. So springs, what else? Ropes only pull. What else? So what other things? Anything else? Yeah. You bet. Free body diagram of a car and bank curve. You want the car facing us or going down the hill? Both. I can't do both when I'm in my same time. So you're talking about, so suppose you got some car, it's got a big bumper in front, all right, and it's got his wheels, and he's on a hill. And I did a silly thing. I made it like at 45 degrees. Well, it's pretty steep actually. Let's say it's 60 degrees, bigger than 45. When I'm trying, as I say over and over again, to make my life easy, I really like to make it. When I'm in my diagrams, I want that to be as horizontal as I can get away with. That's pretty good. And I want to clearly indicate where theta is. I want to make it really clear that this is above 45 degrees. So when I start working out, oh, that's like Lombard Street. Huh? That's worse. This is worse than Lombard Street. Where my right angle is. So yeah, you want a free body diagram. Great. So usually I make a diagram of the situation, and then I make a free body diagram. You're going to label it. You're going to be asked. I'm giving you inside information. You'll be shocked to hear it. Every single past exam is the case. You will be asked to draw a free body diagram. Oh, that's one thing that student asked me now is important. Some of the problems, if you're clever, you can find lots of ways of solving these problems, right? There's lots of ways to do it. In particular, if you've got multiple objects in a problem and they're tied together with a rope or something like that, right? Which often happens on exams. One way to solve it, if all you're asked for is acceleration, is to think of it as a single system and then redraw it, straighten it out, right? Remember so I'm not getting the thing you asked about, but I'm just going to forget. If you have a block over here, there's a problem on a past exam that looks like this, right? There's a block that goes up and down, and there's a block that's hanging. And one student said, well, can I just go ahead and straighten it out the way you did? Sure. But make it really clear to the grader what you're doing. And if you're asked for a free body diagram in part A of the problem for object 1, then give him or her that free body diagram. Don't just draw the free body diagram for the system as a whole because that's the way you solve it. Just so you get full credit for the problem. So if you're asked specifically for a given free body diagram, give us that free body diagram and then proceed to solve it the way you want. If I were you, I'd probably solve it as 2 separate objects and then relate them, right? Rather than doing it as a single system. But it's not a bad idea to think of it as a single system if you're comfortable doing that, to figure out what the answer is before you solve it the other way, just to triangulate. But in terms of the free body diagram for this thing, it's a free body diagram for my car. I chose an angle in this original picture so that I'm looking straight at the car, so there's no perspective in the drawing. You may have a problem where this thing is moving around. Maybe the car's going in a circle around a curve. It's also on a bend or whatever. Choose an angle that makes sense. I think this is what you were looking for. Say, all right, well, how do you do that? Well, he's only going to have, well, let's see, suppose he's parked, and he's got just phenomenal tires, right? Say, all right, well, how many forces are in the problem? Gravity, normal, static friction has to be there, right? Otherwise, he'd be sliding down the hill. So, there's 2 ways I would label gravity. I like to do F sub G, not F times G, F sub G. But if you want, you can label that as m times g. That's fine. If you write m times g, make it really clear it's times g, not subscript g. And if there's multiple objects in the problem, label that m. In other words, if you have block 1 and block 2 in a problem like this, you make a free body diagram, right? So this is m1 over here and m2 over here. When you make your free body diagram for this guy, it better be, if you choose to write mg, well, that's ambiguous. There's lots of m's, right? Make sure you label it m1g, so the grader knows what you, and also, you'll make fewer mistakes. When you go to do the, later on, you got 10 minutes left on the exam, you're going into Newton's second law, it's really easy to make mistakes and put the wrong mass in, you're reading the numbers and stuff. What I usually do is I translate from the written description of the problem onto my solution. I write down m1 equals 3 kilograms, or whatever it is, and I keep it really clear on my diagrams what's what. Anyway, and then, yeah, in this case, there's also some tension, right? That's all this guy's worried about. In this case, you've got FG, and then what am I going to do? I'm going to say, well, let's indicate the force of friction. Do we know at this stage in the problem which way friction must point? Yeah, we actually do, because you know it's going to have to be that way to counter gravity pointing straight down, given that the normal force, which is that way, see, right? And you can write this n or fn, whatever you want, just be consistent with your notation. I like fn, so I mean it's a force. You know right off the bat that the force of friction must be up the hill if the car's not moving, right? If it's holding still. Now, if the car's moving, and if there's something else going on, like if this is part of, this is like a track, like a racetrack, in Indianapolis, where they got the big banked curve that's steep and curving. Now you don't know which way the force of static friction is pointing. In that problem, if he goes really fast, he would, if it were a frictionless track, he'd slide up the top, which sadly cars have done in recent times, right? If he were going really slow, then he would, just like a car parking is really slow, right? He would slide down. And so depending on how quickly he's going around, you might have friction going one way or the other. You may not know at this stage in the problem which way it's going. If that were the case, you could draw it this way, and then, I should label it. It's called force of friction. F sub fr is what I used to use. I often go a step further and put an S. Oop, yeah, that's right, static, because in this problem it's static, right? Just to make sure I use the right mu later on. But don't put the wrong one down. You'll lose points for that. Even if you get the rest of the problem right, they'll ding you after you put it. Right. So yeah, that's how I would make this. Is that what you're looking for? Is there something else to it that you wanted to know? Yeah, right. That's a great question. So if it's moving and you don't know, this is perfectly valid. So is this. As long as it's one way or the other. So how do you proceed? You do that, you make a guess, you put it in whichever of those two ways, you get full credit for this part of the problem, you go to the next part, and then you say, all right, let's, Newton's second law, right? You start plugging and chugging. You got Newton's second law for the x direction, the y direction, you better define your axes, right? Well, okay, maybe I'll choose this for y-axis and this for x-axis. I'll label this diagram, right? And I'll go through it, I'll do for my x and my y, etc., right? And then what I'll do is, I'll stick to my conventions of using this symbol when there's no x or y subscripts to represent the length of the vector. And when the dust clears at the end of all my calculating, if it turns out that I get a negative number for force of friction static, that's the equation telling me that I made the wrong guess at the beginning. Doesn't mean that's okay. I mean, it's not a mistake. It just means you have to interpret it correctly when you get a minus sign. So when you get your minus sign near the end of the calculation, you say, oh, clearly I chose the wrong direction for my diagram. And then when it says, say the direction and magnitude, then you say the direction is the opposite of what I indicated in my diagram. So you can leave your diagram alone. Just make it clear at the end that you know which way the force actually must have pointed, given that you got a negative magnitude when you solve the. So friction, almost it's really our definition for friction. Friction means it's the components of the contact force that is perpendicular to the normal direction. So yeah, you know the friction force is going to be up the hill like that or down the hill like that or into the board. You can have, right? In this class, we avoid 3 dimensions wherever we can, which is actually all the time. It'll always be the case. You can reduce your points. Actually, I say that. There are problems that are 3-dimensional. Like if you got a car going around a curve, that's a 3-dimensional problem, no way around it. But when you actually go to solve the equations of Newton's second law and you write down your diagram, you can always find a way to just make a 2-dimensional drawing that captures everything that's going on. That won't always be the case. Like in 8b, that's not the case. In 8b, it'll be the case where you just have to deal with magnetic field into the board, a velocity that's going that way, and a force that's, you're going to have things going in all 3 directions. In this class, we can pretty much always avoid it. So as long as you choose the right vantage point to draw your 3-way diagram, you make a 2-dimensional drawing, and then you don't have to worry about the fact it's going in or out of the board. It's just going up or down. Well, based on the problem description and everything else. I mean, if the car were speeding up, he steps on the gas, and he's going around this curve, right? Now you've got a situation where, well, let's see, if he steps on the gas, then which way is the force of friction going to be on his tires? Will it be pointing a little bit into the board or a little bit out of the board? So if he steps on the gas, his wheels are pushing that way, so the ground's pushing that way. So the force on the car from the ground is out of the board a little bit due to the fact that he stomped on the gas, in addition to the force of friction that's either going up or down the slope. That's more complicated, you'll probably see on the exam thing. But that's worth thinking. It's just like swinging 2 bats before you go out there to actually swing for real. When you out over into the batter when you go out to play, right? You want to hear some stuff that's a little bit beyond what you'll see. But anyway, yeah. So the way it'll always be, you can find an angle for your free body diagram, a vantage point that's 2-dimensional. It'll often be the case you reduce it to 1 dimension, like this guy. You only need 1 dimension to understand what's going on with this guy right here, because he's only going to move up and down, and all the forces are either up or down. So it's 1-dimensional problem. With this guy, it's necessarily 2 dimensions because you got normal force and there's gravity, and they aren't collinear, right? And there's the tension. So you really need a 2-dimensional free body diagram for him. And when you write down Newton's second law, you have to be really clear about the directions. Well, to be clear in this case too. One thing about notation I'll mention with this problem, the way I solved this was I said, oh, let's call, I forget the directions for my axes, but I think I had a thing over here labeled z-axis that way. And then for this guy, I think I had like an x and a y. It doesn't matter what I did before, I don't remember the details. The point I'm trying to make now is that to make my life easy on this problem, I chose axes that weren't lined up between these two. Because this guy's only moving this way. So, all right, make my life easy. Let's choose it to be a vertical axis. Right? And I gave it a different name.